Hello everyone, welcome to this solving session. So this week content was related to the MOSFET scaling and the technology nodes which like happened like from the invention of Silicon Valley or Silicon industry. And in this session, I will summarize briefly the content which was covered in this week lectures, which you may have gone through online also. So this week content was mostly related to MOSFET scaling and technology node and what are the limits of scaling, like how much we can scale down, is that there is a infinite, and what are the like different characteristics and like some threshold characteristics also, what are the problems. So basically like in the silicon industry, if you see in last 2 3 decade, it's can gone like no other industry has progressed that much, because like nowhere, if you take from example your car or uh, like any in the other in the industry like automobile and those things, the progress is not that much actually. So uh, compared to compare, although progress is there, but it's not that much compared to the silicon industry. So just okay. So then and that has been possible because of the continuous scaling in terms of channel dimension and dimension of devices, and also that leads to more like computation power you can pack in per unit area. That is still way behind compared to the normal human computation or whatever, like the natural computation machines. We are still not that much, but it has seen a growth, unprecedented growth, which is not there in almost any of the industries actually. So the fundamental like in 1950s actually, the after the discovery of transistors by William Shockley and others. So then basically like they invented BJT, and then after some time when the process get stabilized and people started taking, because then now the process was the growth process and other process was better. So people started taking interest in other kind of fat devices, I think. So earlier the fat was not possible because the material growth was not that stable compared to what the interface, what the current industry and those demands. But the but after like after the invention of uh, transistors, like around 1960, people started looking to beyond the normal conventional BJT and those bipolar charges. So then basically, and then the founder, like the Shockley founded a company like that, Shockley Semiconductor Labs, and there is a story called Treacherous Eight, and they founded a Fairchild Semiconductor, and then like they like one of them was the Intel founders, which whose name is Gordon Murray. His name is Gordon Murray. So he gave a prediction that every 2 years, so every 2 years, the transistor footprint print uh, become like the every 2 years the number of transistors in the chip will get doubled, and so the efficiency will also get doubled, and also the cost will become lower. And this trend was fairly like for 3 4 decades, it's a trend goes on actually, and up to now this trend is going on, but it's kind of saturating. We started to hit the like the normal physical limits which the scaling is possible. Even like different point of time, people started like that, now the saturation had hit. But like the silicon industry, because demand is there, everyone wants more phone, more computation power. So like that demand is, because that demand is there, so that's why still people are trying to revive the Murray's law. So basically, what it tell that like every 2 years, your number of transistors in your chip will get doubled, and so the your performance or computation will increase twofold or every 2 years, and then the a similar trend. And this was not a law based on some physical parameters or physics or anything, but it was just a prediction actually. But this carried on throughout the last 30 or 40, last 3 or 4 decades. So the main driver behind the this scaling was the scaling of the MOSFET. So every 2 year you basically scale down the MOSFET. Previous you just reduce the dimension by half, and then you increase more and more density, and then you increase more and more computation power per unit area. So that was uh, the scaling, and then basically your so then so basically now as you scale down the devices, you will so you basically what are the implications actually? So let's draw the diagram of this MOSFET. So to shrink down basically, so basically this is the channel length L, and this is the oxide thickness T ox, and this is the uh, so and this is N plus region, this is P type substrate, and these are the gate connections. So these are the gate connections, and so basically now basically what you do, you scale down the MOSFET, and then uh, so so basically, your current, or you can your if you can see your current equation. So your drain current is basically given as mu n cox W by L times times, if you take in the saturation region, it is equal to VGS minus VT times VDS minus VDS square by 2. This is the current. And if you take COX, you can replace as mu n COX. COX is basically epsilon ox. This is gate capacitance per unit area. And this is T ox, and W by L times VGS minus VT, and the threshold voltage turn. So people like in the throughout the industry, throughout the lifetime, people have explored different like this is very oversimplified picture, but people has used uh, different parameters in this equation. So initially, to get higher current and to get this, people started reducing this ratio, or people keep reducing channel length. But as you reduce the channel length, actually that other short channel effect start to play out. And then like the earlier this basically they were using planar MOSFET, and then basically if you keep reducing the channel length, you get higher on current. And basically you can get if you reduce this W by L in together, then your on current will remain same, and you will get same performance with less area. So people were happy about this up to 28 or 90 nanometer technology. But after the 19 nanometer technology, this channel length scaling was not enough because because what happens is, so ideally what should happen in the MOSFET. So let me draw the band diagram. So in a MOSFET, ideally there should not be any current. Like when you apply a 0 volt gate voltage, there should not be any current. But what happens is there is some leakage. So now what happens is, let's say you did not apply this gate voltage, so you have a barrier between this electron and between source and substrate and drain and substrate. And then basically the electron needs to overcome this barrier to take part in the conduction. But when the channel length was there, so ideally in your switch, the best switch is, suppose you this is the switch and this is controlled by a gate voltage. So ideally when you don't apply any voltage to gate, there should be any zero current should flow actually. And also the for a switch, when you don't apply a gate voltage or you don't apply the control voltage, there should not be any depending like irrespective of the voltage applied to flow the current, there should not be any leakage current, or current should not change. This was the story when the channel length was in the micron range, or those kind of dimension. The people were happy and they were keep reducing the dimension. But after a certain times, what has started to happen, when they reduce the dimension below a certain dimension, so what happens is, so this ideally this drain should not the drain should not affect the threshold characteristics or turn on characteristics. But like as you move slower and slower, lower and lower dimension, this effect started to come. Basically now this source to drain barrier get started lowered down by applying the higher drain voltage. So basically, like if you apply higher drain voltage, then your drain to your substrate to source barrier get reduced, and you will see a flow of current, and that will contribute to leakage current. So up to now, all people were happy that like there are no problems. And like the but like after some dimension, the up to the 90 nanometer, people thought like it's not like physically it's not possible to scale actually, because this gate drain induced barrier loading, because of the drain induced barrier loading, drain induced barrier loading. So because of this, people start like seeing uh, the normal and this was known as the normal Lennard scaling. So Lennard was one of the, I think, industrialist order. So normal Lennard scaling. So you keep shrinking down the dimension and you can achieve better performance, and then basically you will get more and more performance. But after this Lennard linear dimension scaling era got saturated, people started focusing on other parameters like the mobility. So, as you know, like the 90 nanometer Intel introduced a silicon germanium technology in which they strained the silicon layers to get enhanced mobility. So, one generation they changed the mobility also. Also, there then you can reduce this oxide thickness also. To if you reduce the oxide thickness, then you will get higher current at lower voltage actually. So the for certain technology, people started trying out this new oxide or different oxide. People keep reducing the oxide thickness, but like after the thing, like after a certain thickness, basically this oxide will cause a leakage current to the device, because if you put if you reduce the oxide thickness, then basically this drain leakage, the gate to source or gate to drain leakage current will get increased. So that also has limit. Then people started exploring this other parameters, which is dielectric constant of the oxide material used. So people started using different dielectric with high K dielectric, basically. So it can provide same dielectric effect. Basically, if you use higher K dielectric, then you can get higher current, but you will you will see. And also the threshold voltage is also a function of the gate dielectric constant. So if you keep using higher dielectric, like for example, for certain technology nodes, people started using this hafnium oxide, which has dielectric constant of 35 around, or 30, in the range of 30, and the comparison to normal silicon oxide, which is around 4 or 5, that people get like more room to play out with. So that basically so people throughout the generation, people started exploited this all these parameters to make that like Moore's law trend workable. But now again, like every decade, there are different number of challenges and different number of uh, problems are there. So now, like after that, basically, people started using. So instead of planar geometry, people started using started changing the architecture. So now, in the those 22 nanometer node, introduce a tri-gate kind of structure. So in which the channel was the surrounded by the gate from three sides, actually. So they named it as the tri-gate. So what was the advantage of this device? Because so in the planar, you basically your gate area is limited by the planar area. But in this, you can make like a fin kind of structures, and those you can make like fin kind of structure, which is used for FinFET. And in that, basically, you can achieve more gate control, which allows for more for better gate control, and you will get more sub-threshold slope, and then you will get more on-off characteristics. So I on by I off is better, because you will get higher sub-threshold slope, or sub-threshold slope reaching to near ideal case, or reaching to 60 millivolt per decade slope. So one generation, then they try this, and then then next, this was the tri-gate, and then people started using multiple fins, and then multiple fins, and then like some TSMC and Samsung, the newest foundry, they are using nanosheet kind of MOSFET, where they stack the channel vertically in the vertical dimension, multiple channel in the vertical dimensions, and then they move the technology much forward. Even like next of those, like the fork sheet kind of architecture are also there. So people are doing like different experiment with the architectures, and like the challenges are quite high, because like this dimension has reduced up to like few nanometers, and like 40 or 50 kind of nanometers they are approaching. So your like here like if you want to study if you want to know a rough idea about the dimensions, basically dimension, your hair size is around 24 micron, and if you take the 24 micron, your hair size is 24 micron, and if you keep dividing by 10, and you will reach, see, like 24 nanometer is basically just 10 order of like 3 order of less compared to this. So if you divide your hair in, like if you analogically say divide in thousand parts, then you will reach the dimension of current transistors. So it has reached up to that level. So that is the that is the Moore scaling, and uh, different kind of. So so the basically so limit there are fundamental limits to scaling. So basically you can't reduce the channel length up to a certain distance, below a certain channel length, because then uh, your channel length, those drain induced barrier lowering DIBL effect will start to play out, which leads to higher leakage current, and which leads to more more you say more off state power leakage. So now like instead, and then you can reduce this the oxide thickness, but the oxide thickness, then your gate leakage with current will also get introduced, increased also. And then you can play out with different subthreshold swings. And if you get a better control compared to like the FinFET kind of geometries, where the gate control is higher compared to other, then you will get a better compared to the planar MOSFET technologies. And also people has tried this FDSI kind of technology, where this fully depleted silicon on insulator transistors. So basically what you do is you insert a channel, and you insert a oxide from both sides, and you allow from both, from the top and from the bottom control, and you can get some better characteristics compared to normal planar MOSFET. But this was also not much, because like there were a issue with the SOI process, because like you need for a industry you need higher supply volume of the wafers, but that SOI process is not that standard compared to the normal silicon process. So that was the limits of scaling. And basically your threshold voltage. So if you can see, the threshold voltage is given as so you can threshold voltage you can define as the as the voltage across the oxide. So you can define the threshold voltage as so threshold voltage, if you define, then basically the drop across oxide plus drop across silicon. So this silicon drop across silicon you can just replace by the so this you can just replace by your in terms of your surface potential. If you drive this, so basically to get this silicon voltage, you need to find what is the surface potential in the depletion region. So that basically, if you take this MOSFET structures, you can find it like this surface depletion, and that with the after applying this boundary condition at the dielectric semiconductor interface, you will get the drop across the oxide region also. So with this, like this epsilon of SiO2, you can, or oxide, you can calculate, and the field in the silicon region at the interface you can calculate. From that, you can calculate what is the drop across the semiconductor region. So basically, like so uh, so you can calculate like this. This the surface potential psi of S at threshold voltage is basically equals to 2 psi of F, and which is equals to kT ln of Nd by, or Na by Ni. And that surface potential will drop across the semiconductors, and this surface potential will be equals to the area under this the electric field plot. Then that will be the half of electric field at the silicon dioxide or silicon dielectric interface times the depletion rate. And depletion rate you can calculate by the depletion width. You can calculate how much is the your with this surface potential drop, and that basically is given by depletion width is given by your square root of q and d by 2 epsilon uh, uh, 2 psi f. Basically, it's given that is the depletion rate. So basically, you can get the surface potential as, and also you can get this oxide voltage also you can get. So this surface potential drop basically the also this e silicon you can calculate from the boundary condition. If you apply, then it is basically also equals to q and d q and d n a or n d by epsilon times x of depletion. So this, if you put this, then you will reach half of q and a times epsilon times w depletion square, and that w depletion square you can replace from here, and there you can get the threshold voltage equation. So that is so the threshold voltage is inversely proportional to the also this oxide. So this is the you can get the voltage is epsilon ox times the field in the oxide region times c t ox, and field you can define as in terms of oxide capacitance and voltage across the oxide that you will get, and that basically your threshold voltage is a function of your oxide voltage actually. So the how much surface potential you are applying it, that is dependent on your the threshold voltage is dependent or the of the oxide or the dielectric constant which you are using. So that is your threshold voltage equation. So yeah, so recently people started this vertical kind of geometries, and those kind of exotic kind of structure people started exploring, and those are different scalings are possible because of these parameters. So this was the brief summary of this week content. We will start solving the problems now. And if you have any doubts related to the content uh, which I covered or which I covered in the next week, so that basically you can get started. So then basically so let's just move to straightforward problem solving session. So so the first question is, who formulated the Moore's laws, and what does this predict? So that was the straightforward question. So it was the correct answer is it's a historical question only. So the correct answer is Gordon Moore predict. It predicts that the number of transistors in a microchip will double approximately every 2 years, leading to exponential growth in computing power. So if you increase every 2 years, it's just like that exponential growth, and that leads to the very efficient computing power. So this was the this was the more historical question. So the next problem talks about the evaluation of various technology nodes over the years is given in figure below. The technology node, as you can see, every 2 years, like every year actually the nodes happens, but like there is in between a half node is there. So so they see like that 65 is get after 2 years this goes to 35, and that's 45 reduced to 22. Similarly, 22 reduced to 10 and 14 reduced to 10. So then next you can reduce 10 reduced to 5 and then 7 reduced to 3.5 or 3 nanometer. And then this 5 reduced to 2 nanometer. So that basically so that was the trend. Comment on the power dissipation from technology node from uh, 90 nanometer to 90 nanometer, 250 nanometer to 90 nanometer. Consider the alpha is the scaling factor on each of the nodes. So basically, what I need to see was for 250 nanometer was here and the 90 nanometer was here. So then basically at each node the scaling down is the so at each node, basically, the power is because it's square. So in between three nodes, like 250 to 180, 180 to 30, and 30 to 90, and because the power is uh, uh, power is basically power is scale for each scaling by alpha time, power scales by alpha square time. So basically the power will get scaled by the alpha 6 time. So each node basically the power scales by alpha square times, and corresponding the answer will be the power in the 90 nanometer will be equals to the power in the alpha to the power 6 times the power in the 250 nanometer. So that was the correct answers, and so uh, so with that, let's move to next problem. This was pretty straightforward. With that, let's move to comment on the gate capacitance per unit area in the technology node from 250 nanometer to 90 nanometer. Consider alpha is a scaling. So the epsilon ox gate capacitance is basically epsilon C ox is basically C ox C ox is basically epsilon ox divided by T ox, and if you T ox, if you scale by alpha, then basically in the oxide capacitance in three generation it will get scaled by alpha cube, and that is your correct answer. So the correct answer will be C ox will be uh, if your dimension reduced by your uh, if your dimension reduced by this, then basically your the gate capacitance will reduce by alpha cube actually. So this so gate capacitance C ox at 90 nanometer will be 1 by alpha times cube times C ox at 250 nanometer. So the correct answer is this one. This is alpha cube, not 3 alpha. So then basically this is the correct answer. It will reduce by alpha cube, not this 3 alpha. So this will become C ox times 250 divided by alpha cube. That is the correct answer. So let's move to next. So choose the correct statement regarding to constant voltage scaling. So basically, uh, you in the constant voltage scaling, you will keep the power supply as a constant. So uh, so uh, so uh, uh, let's choose the option. So the supply voltage was scaled same as the dimension of the MOSFET. This was wrong because the voltage scaling you will want to keep the voltage as the same, voltage of the operation as the same, while while reducing the dimension. So so basically, next option is supply voltage was kept constant to maintain sufficient high and low margin. This is correct. And threshold voltage was scaled down to double the dimension of the MOSFET. So that was not correctly true, but how the threshold voltage will scale with the constant supply voltage scaling. Both the so it is not true because in the constant voltage scaling, and both the supply and threshold voltage get increased. So this is wrong because the you want lower and lower threshold and supply voltage actually, because if you want to operate for a low power device, you want to operate as less power as possible. So now, because when you pack more and more transistors per unit area, then if you use larger dimension transistor, then power density is larger, then the power dissipation is just increased. So basically, you want to keep the supply voltage also in the same trend, and as you reduce the dimension. So then threshold voltage was kept constant to make high on to off ratio. So this was the correct. And the correct options are second and third one. Second and last one. So in a so let's move to next problem. So the next problem talks about in a short channel MOSFET, as the VDS is increased, the effective channel length LF is and the total drain current decreased. So in the short channel length, basically your so basically what happens is like in when your channel length is short, so basically this n plus and this n plus and this p substrate region is there. As you increase as you as you increase the drain to source voltage, so what happens is this source side depletion will become more uh, just wait. So this basically this side depletion will get more and more, and your effective channel length basically reduces. So basically your channel length L effective will get decreased, because now that because as you apply higher and higher voltage, earlier because the channel if the channel was larger dimension, then this depletion width does not affect, but nowadays like this depletion width is in the order of the total channel length. So if you eat up the a part of the total channel length, then basically your effective channel length will get reduced. So basically L effective will get reduced, and basically what happens is your drain current will get the total drain current will get reduced, because now the you have less channel length, and the your saturation voltage will get increased, and so saturation current will get increased because you have now smaller and smaller uh, channel length, and that your because id is inversely proportional to square root of L effective, and that as you increase the drain to source voltage, your current will as you reduce the effective channel length, your current will get increased. So basically, the correct answer is effective channel length will get decreased and drain current will get increased. So other options are effective channel length get increased, drain current has increased. This is wrong. Effective channel length increase and total drain current get decreased. This is also wrong. Effective channel length and total drain current remain constant. Effective channel length remain decrease and drain current remain constant. This is also wrong. Effective channel length remain constant and total drain current can decrease. This is also wrong, because effective channel length reduce that the drain current is the effect of that. So this the correct answer was this. The channel length and drain current, effective channel length decrease as the drain current increase. So this so the so if you have any doubt, you can ask. I will pause for some time. So let's just get started. Yeah. So let's move to next problem. So consider a two MOSFET M1 M2 and the following dimension. M1 has a length 8 micron and width as a 2 micron. Oxide thickness is a 200 nanometer. M2 has a length as zero point 0.8 micron, width has a W 8 micron and thickness is 180. The electron diffusion length is 1 micrometer. Choose the following option. So basically, you need to compare what is the channel length compared to the diffusion length of the electrons. If channel L channel length is less than diffusion length, a diffusion length basically what is the diffusion? How the diffusion happens is basically your carrier collide with the core shell ions, and that will the electron will take a random path. But if you are operating at a length which is less than compared to the diffusion length is defined as uh, the the path traveled by a particle before next collision, or path traveled by the particle between two different collisions actually. So then if that like the that collision diffusion length is large compared to the channel length, then basically the carrier won't collide throughout the when it passes through the channel. So basically, like that, those velocity saturation and those kind of effect will be there. So we need to find like which channel which is which is the which is like the short channel MOSFET. So as in case of first, L1 which is 8 micron is very large compared to 1 micron. So this is M1 is long channel MOSFET, and L2 as you can see it's zero point 0.8 micron, and which is less compared to 1 micron. So this is a short channel MOSFET. So M1 is a short channel MOSFET. This is wrong. M2 is a short channel MOSFET. This is correct. M1 is a long channel MOSFET. This is correct. And M2 is a long channel MOSFET. This is wrong. And M1 is a tunnel FET. This is wrong. This is does not make any sense. So this was the problem. So basically, you need to look at the channel length only. Not other parameters are not that relevant, particularly in this problem. So that basically is the answer to this question. So let's move to next problem. So the IV of a short channel MOSFET is shown to scale in the figure below. So basically we so if the channel length is triple to 3L1, choose the correct IV characteristics uh, from the uh, from the options below. So if you increase the channel length, basically your saturation. Your in the long channel MOSFET current remain constant uh, after the saturation. So basically, so this in this also the current increases. Only the option in this and this the current remain constant. So these others options are wrong. And in also in the other MOSFET, basically the current will get the the saturation basically, if you increase the channel length, basically the current will get reduced because I is inversely proportional to 1 by L. If you increase L by 3, so your current is roughly reduced by the the current is also reduced by the by a factor of 3. So that from that option, the D option is wrong because the in this current is getting increased. Also from A and D, because like now your the edge of the saturation region will also get increased because now you it will take larger voltage for your channel to get pinched off. So between A and C, the correct option is A because like the it is like the saturation voltage hits at larger gate voltage compared to C option. So the correct option is C. Correct option is A because this. So as you can see, it will take a larger to pinch off the channel. It will take larger drain voltage for channel having larger channel length. So that was this problem. So if you have a doubt related to the problem, then you can ask. Otherwise, we'll move to next problem. So this so basically yeah. So this so let's move to next problem. Choose the reasoning of the previous question. So basically, why the uh, choose the correct reasoning for answer in the previous question. The current for a long channel MOSFET saturated larger VDS compared to the short channel MOSFET. This is correct only. The long channel MOSFET reaches at the critical read at larger applied bias in the absence of velocity saturation. This is also correct. Basically, it just the current for a long channel MOSFET saturated as a smaller VDS. This is wrong compared to the short channel MOSFET. This is wrong. The long channel MOSFET reaches at the critical feed as smaller applied bias. The long channel MOSFET reaches at the critical field at the smaller applies bias leading to velocity. No, this is the inverse is true actually. So if you take the channel length, so if you have smaller channel length, then your field will be your field across the this channel is basically VDS by L. So roughly you can define as VDS by L. So if you keep VDS as constant, if you increase L, your field will also get reduced actually. So that this is a wrong option. And ion by I of current ratio for MOSFET channel is low compared to the short channel MOSFET. This is also uh, uh, this is also the l- current ratio for long channel. This is also not correct because the long channel MOSFET has better gate control compared to the short channel MOSFET, which has drain induced barrier lowering and other type of short channel effect, which have like the long channel MOSFET has better I1 by I of characteristic. The current in the long channel MOSFET follows a square law theory. The uh, the correct option is because see, like the IDS is basically VGS minus VT, and as you can when this VDS equals to VGS minus VT, then basically your IDS will get increase after this. So basically, edge of the saturation is dependent on your drain voltage. So basically, that is a square root dependence, and that last option is also correct. Sorry, that is not a square root dependence. It's parabolic dependence. So that with that, let's move to the next problem. So this so given a few statements regarding the FinFET technology, choose the correct option. FinFET offers a better electrostatic control. So basically, what is the electrostatic control? So like this, basically, what you apply the gate voltage to turn on the transistors. That is basically the electrostatics, and what you apply to other like in the to apply the flow the current, that is basically your turn on characteristics. So basically in the in the MOSFET, because gate is surrounding by this, so this field is penetrating in this like this from the three direction. So it has a basically better control compared to the planar MOSFET, which has only single phase gate control is there. But in this like the gate gate it has better control compared to the normal MOSFET. So that basically that is the correct answer. The FinFET has lower I to on ratio than the planar MOSFET. So basically, like this I on by I off is not impacted basically because that it can be true also. No, no. So that because that is a function of your how much leakage current is there. But since for a long channel MOSFET or the FinFET, basically ion and I off ratio is not better. The FinFET has a lower leakage current than the planar MOSFET because the gate voltage has the gate surrounding from both the dimension. The FinFET has a better leakage current because you can use higher gate oxide and those. So the answer C is also correct. For a similar operating voltage, planar MOSFET offer much lower delays compared to the than the FinFET. So that is also not generally can be true. So this is also not correct option actually. So in certain exception, this way may not be valid. So the correct option is A and C. And the so this so 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 with this, let's move to next problem. So what are the technological node which is currently being used in Samsung smartphone Snapdragon 8? So although this is a Samsung smartphone, but this is talking about Snapdragon 8, and the Qualcomm for their 4 nanometer process use TSMC. Uh, so that basically from among the options, basically the Intel 250, that Intel is nowhere closer. Intel 7 nanometer node, no, that 7 nanometer is old at S10 S10 times Samsung 14 nanometer, that is also wrong. Samsung 10 nanometer, that is wrong. That was over like before S10, like S5 or something. So the current is like this TSMC 4 nanometer technology because Qualcomm is the like the TSMC the vendor for like all those smart Samsung like the Snapdragon 8 Generation 8 processor. So that basically uses the TSMC process compared to the Samsung. So although the phone is Samsung, but the answer is TSMC. So this was the problem solving session from today's discussion, and the discussion happened over this week. So please go through the slides and others other important please go through these problem solving sessions, and uh, this was the session like this was the last problem from my side. I will pause for some time if you have any doubt, or then I can answer any your queries. So this was the mostly this week mostly it was about the historical context and some trends basically related to the technologies and those process. So that was the main content which I was about to give. So if you don't have any further doubt, then we can end this session for today. And till then, you and keep enjoying learning and have a nice week and have a great learning. Till then, thank you so much for listening this session, and we will meet next time in the same session, same week at the same slot. Thank you so much. Bye. Have a nice time. Good night.